Good afternoon, everyone. My name is Dr. Kevin Stinson. I'm an infection control practitioner at St. Mary's General Hospital in Kitchener, Ontario. Today, I'm going to be doing a talk called COVID-19 Vaccines, Myths, and Facts. This is a talk I've given a few times to various groups in healthcare and a few groups outside of healthcare. And what I aim to do with this is really dive into the science and the technology behind these new COVID-19 vaccines and debunk a lot of the myths and the big questions that are very often raised with them. What I always like to start off with is a look at how does the body respond to a viral infection in the first place? Because this is where we're going to have a lot of our common ground between natural infection and a vaccine response. So of course, the big players that we're going to be looking at for a viral infection is a cell. So in this case, our nice respiratory epithelial cell and our virus. So this is our lovely COVID virus. We have all these nice little spike proteins in red on the cell surface. Now, in order for that virus to bind and enter a cell, we need a cell surface receptor. In this case, it's ACE2. So ACE2 is expressed on the cell and binds to a portion of the spike protein called the receptor binding domain, or RBD. Once you have that binding, the virus can be taken up into the cell. The nucleic acids, in this case RNA, is released into the cytosol, and then that is converted or is used to create new proteins, and those proteins get assembled into more virus that can then be released out and go on to infect other cells. So that's that normal process of viral infection. Now, this is something that is very foreign to the body. The body's not, or rather, cells are not used to something that is not self entering in and replicating inside of it. So it has defenses that are designed to identify foreign protein and foreign nucleic acids. So the way that it does that is if we take our lovely RNA molecule there and we create this lovely molecule of the spike protein, the body can recognize this as foreign and sends off enzymes to go and digest this protein and what we call process it as an antigen. Now, those individual little antigens can be taken and displayed on the cell surface on a molecule that we call MHC class 1 or MHC1. So this is how our body recognizes that something's foreign and in essence flags the immune response to say, hey, I have something foreign growing inside of me. I have a viral infection inside of me. I need help. And the way that the body does, or the way that the body responds to a cell that's infected like this for help, is it calls in a cell called a cytotoxic T lymphocyte. So these cytotoxic T lymphocytes go around trying to find these cells that are expressing an antigen on their cell surface on that MHC class 1 molecule. That cytotoxic T cell will go bind, release a large amount of cytokines and chemokines and other small proteins, and in essence, triggers that cell to kill itself through a process called apoptosis. And this is the natural response to a viral infection. The body says, all right, or rather the cell says, all right, I'm infected. I need help. I need someone to please come kill me because if I'm infected and this virus is inside replicating, eventually it's going to kill me anyway, and then it's going to potentially infect my neighbors down the cell line there. So this is the way of controlling infections early. Now, the other thing that's nice about this is this nice now activated cytotoxic T cell goes off and does a process called clonal expansion, where it says, all right, I've been utilized. So clearly, if I've been utilized, my particular type of T cell, the specific antigen or protein that I recognize is needed, I'm going to go off and make copies of myself so that as more cells become infected, we have nice, faster coordinated response in the future. Now, what very often happens in COVID is because we've never seen COVID before, a lot of these cytotoxic T lymphocyte responses are very slow to initialize and very slow to react. So the cell can have a bit of a sideline or an alternate pathway to fixing this problem. So the cell's sitting there signaling on that MHC1 molecule, hey, I'm infected, please come help me, please come kill me, and nothing's coming, no one's coming to help, nothing's happening. The other thing that a cell can recognize is as this RNA molecule here is replicating, we get a very, very typical viral construct called double-stranded RNA. Typically, we only really see this in nature during viral infection, or usually. So when the body sees that, the body or the cell knows that this is now a viral infection. And what the cell can do is say, all right, I've called for help. No one's coming to help. No one's coming to help. No one's coming to help. All right, I'm going to activate a whole alternate cascade here. I'm going to activate a process called pyroptosis, which in effect is going to do that same job of killing the cell. But what it does is it does that in an extremely inflammatory process. So in essence, what the cell is saying is no one's coming to help me. If no one's coming to help me, that means no one's coming to help my neighbors. So with no one coming to help my neighbors, what I'm going to do as a response is I'm going to kill myself and release a massive inflammatory burst and hope that I can recruit a whole bunch of immune cells to this tissue, and they can all help my neighboring cells out. The problem is when you look at COVID, and we get this same response happening all through the respiratory tract. That's what takes you from a nice, typical upper respiratory tract viral infection and brings you into a respiratory pneumonia, because you have a large amount of cell death and a large amount of very pro-inflammatory cell death driving inflammation. So that's a little bit about the kind of general background of how does the cell recognize that it's infected, and what's the kind of response on the cell level to that initial infection. So this is a process of immunity we call cell-mediated immunity, but it's only about half the story for the antiviral immune response. Because as I'm sure everyone is well aware, the real thing, or the other thing that we want to see out of an immune response is antibodies. So we have our virus here, our lovely little COVID virion, and we have a professional macrophage or a professional phagocytic cell. So in this case, a dendritic cell, a cell whose job it is to identify foreign bacteria, viruses, particles, whatever in the body and swallow them. So when the dendritic cell does that, it does a lot of that same process of swallowing that foreign body, processing a lot of the protein, and displaying it on one of those cell surface receptors. This time, it's an MHC class II molecule. This has a little bit of a different approach. So this one isn't going to trigger those cytotoxic T cells to say, hey, I'm infected, please come and kill me. This is going to go for a different type of T cell. It's going to go for what we call T helper cells. When T helper cells bind and recognize that processed antigen on MHC class II molecules, what happens is they become activated. And they can now then go and find a B cell that's expressing the same thing on a cell receptor. I'm skipping a few steps here, but in generality, it's going to go and off and find a B cell that's expressing that same protein, and it's going to activate that B cell and stimulate that B cell to start differentiating and producing antibodies. So as this process happens, of course, it's the antibodies that then, when you take that COVID virion, will then bind up and either neutralize the virion, so they bind to that receptor binding domain, the RBD domain of the spike protein, and physically block it from entering or from connecting to the cell and being able to enter the cell. Or they stick it all together so that cells like our dendritic cells can better identify better catch that there's virus there and swallow it up and engulf it up and phagocytose it and destroy it. So this is what we call the humoral immune response. So good, proper immunity does very much rely on both of these. The humoral immune response is going to be what hopefully prevents initial infection. So the idea is, if I have neutralizing antibodies in my body or in my sera, if I have COVID coming in, those neutralizing antibodies can recognize, bind, and neutralize the virus to prevent it from causing infection. If it does cause infection, I want those cytotoxic T cell responses, those cell-mediated immune responses, to be primed and ready so that I can very effectively and rapidly identify that a cell's infected and kill that cell prior to the cell going down those alternate pathways that we talked about, that pyroptosis pathway where it in essence kills itself in that very dramatic pro-inflammatory or hyper-inflammatory response. So these are the two real arms of the immune system. Now, from a vaccine perspective, typically we've only seen two types of, or primarily seen two major categories of vaccines to date. We've had live attenuated vaccines where you've taken a virus and you've weakened it. It can enter a cell, it can cause disease, but the idea is it's weakened to a point where most people who get it won't have any disease. The immune system will bind, recognize, activate all these cascades, and you'll have your immune response. This is really falling out of favor lately because one of the big issues is if I'm immunocompromised and you give that to me, if I don't have that strong immune response, there is actually a good possibility that I become infected, or at least I have some degree of disease. So when we look at most vaccines right now, most vaccines are what we call an inactivated virus vaccine. So we think of the flu vaccine, that is a killed, inactivated flu. So they take the virus, they kill it, and they infect or inject that into your body. So when that happens, this process here, the humoral immune response that you see on the screen, this will all happen really, really well. But what doesn't happen is the virus will never enter into the cell because it's inactivated, it's dead. It really just can't enter the cell and it can't stimulate a lot of those cell-mediated immune responses. So that's always been the holy grail of how do you get a vaccine that is both safe and broad enough that it stimulates both arms of the immune system. And that's where we enter the advent of mRNA vaccines. Now, we say mRNA vaccines are fairly new. COVID is, of course, the first time that an mRNA vaccine's ever been live onto the market, but the technology's been in development for about 30 years now. And I think the initial, if I recall correctly, the initial clinical trials of mRNA vaccines were as far as the late 2008 to 2012, somewhere in that area. So the mRNA vaccines, the way that these are designed is you take mRNA, so the intermediate between DNA and protein, and you encapsulate it in a lipid nanoparticle. And what we can do is we can take just the mRNA for the gene of interest. So in this case, for the COVID vaccine, we're looking at the spike protein of SARS-CoV-2. So we take the mRNA of the spike protein, we encapsulate it in lipids, and we inject that into the body. And as you can see on the pathway A here, these lipid nanoparticles containing the mRNA is taken up into the cell. The mRNA is released into the cytosol and is processed into these lovely proteins. And then we see that same process that we saw earlier. We have that digested by the body, bound to that MHC1 molecule, and expressed on the cell surface. So we know right now that what this is going to do is it's actually going to go off and recruit cytotoxic T cells to recognize that this is, hey, that's the help me signal, I'm infected, please come kill me. And by doing that, prime those T cell responses to go through that process of clonal expansion and make more copies of themselves. The other thing that we get is as cells are killed through that process, you'll have some degree of this protein that gets released into the cytosol. And that's what we look at right here, where we have this exogenous protein that's brought in and is processed and displayed on that MHC class II molecule. And that's going to be that molecule that then is used to prime that humoral immune response, the antibody-mediated immune response. So those T helper cells, and then through that, the B cells, and generating all of our antibodies. So that's the real advent of this vaccine. This is a vaccine that is safe. It does not have live virus, but it still has the ability to trigger both halves of the immune system. And the other type of vaccine that was or that's in the media right now is the AstraZeneca vaccine, the Johnson& Johnson vaccine. That's a very similar technology. Instead of it being an mRNA vaccine, it's what we call a replication deficient adenovirus vector vaccine. So what they do for that is instead of it being, so replication deficient, right in the name, you know it cannot replicate. What they do is they take the genome of an adenovirus and they chunk out all of the stuff that's going to allow that virus to replicate, and they put in a transgene, something that they want to express. In this case, it's the spike protein. So once we have that transgene in, it gets encapsulated into an adenovirus and injected into the body. It then has the ability to infect cells. And then once it infects cells, this exact same process takes place. It's just instead of it being mRNA, it's DNA instead. So very, very similar technology once it physically gets into the cell. The only real difference is how does it get into the cell in the first place? So that's our kind of background on how do vaccines work, how do these vaccines work, and kind of really dive into the immune responses against viral infection. So now we get into our myths and our facts. So the first myth that I hear quite frequently is that the COVID-19 vaccines were rushed, and they did that by bypassing safety measures, and as such, these are unsafe vaccines or untested vaccines. I think is the way that people like to say it is these experimental vaccines. And in reality, so these did come out fairly quickly, and there's a reason that they came out fairly quickly. If we look at the top three front-running companies, so Pfizer and Moderna, as well as AstraZeneca, all of these three companies had a vaccine in development for MERS-CoV, which is a very, very similar, another very similar coronavirus of bat origin causing very similar disease. So when you have all that fundamental core science already done, the animal trials are already done. In fact, some of them had already been through phase 1 human trials. It's very easy to just say, all right, we're going to take out the one protein, put in a new protein, and we can immediately restart the animal trials. All of the fundamental background science has already been done. Because that's the big thing, is a lot of what takes time to develop a new drug is not the actual clinical trial process itself. It's the 30 years of background science that leads up to that clinical trial that really delays things. So all of the vaccines that are being approved by Health Canada or even in the approval process have gone through a full 3-phase clinical efficacy and safety trial. So none of these have bypassed or skipped any of those efficacy trials. Now, what potentially has been accelerated is the actual approval process, not from the perspective of we're going to accelerate or bypass safety measures and checks and balances in the approval process. But what's happened with a lot of things in COVID-19 is, and we see this in research and administrative approvals, is everything has been basically put on hold. So from a drug trial perspective, for example, all drug trial applications that typically have about an 18-month waiting list are on hold. And now anything with COVID-19 written across the title skips that long waiting list, and we immediately take and start reviewing. So it's not that you're skipping the approval process. You're not skipping any of those standards approvals. You're just skipping the line to get to that approval process, which makes it seem like a much faster and more expedited process. So the other thing that, fortunately, this one's slightly starting to fall out of favor, I think, in a lot of the media and social media, but the idea that mRNA is going to alter your DNA, or that these vaccines are somehow a genomic modifying vaccine. And they hear the idea that there's nucleic acids in it, so it must be genomic modification. And I think it's important to understand, well, first, what is mRNA? So mRNA is, of course, the midpoint between DNA, our nucleic acid code, and protein. the actual, well, physical effectors that make our body our body. So the reason we have that intermediate is there's a big component of how do we regulate protein expression. You have this unstable intermediary, so that if I want to create a protein like spike protein, I have, or a bad example because that's an RNA virus. But if I wanted to create a protein as a human, I have my DNA genome. I create a copy of mRNA as a intermediate that can then go and create several copies of DNA and eventually breaks down. If I want to keep expressing that protein, I need to keep creating more and more copies of that mRNA. So that's the kind of general process of how mRNA fits into our expression, or into protein expression. So in order for that mRNA to alter your DNA, we have to go through a process called reverse transcription, where the RNA or the mRNA is converted back into DNA and then is able to integrate into the cells, which is an actual biological process. It does happen. We see that with things like HIV, a retrovirus, where it's a RNA virus that once it infects the cell is reverse transcribed into DNA and then has the ability to integrate into the host genome. Simply put, these vaccines lack multiple steps required for that. For one, they lack the reverse transcriptase, which is not naturally produced by humans, and they lack the ability to then integrate into the human DNA. So without those steps, really, there's no physical way for that process to actually happen. The other thing to consider is, like we said, mRNA is a transient intermediate. It's designed to be unstable so that if I want to keep expressing a protein, I have to keep creating mRNA from that DNA. So once that mRNA is actually in the cell, it's going to break down pretty quickly in the matter of hours to days. So very, very quickly upon entry, it's already starting to be degraded. And we'll kind of talk about that a little bit as to why we have such weird storage conditions in a few slides. So even any mRNA that's lingering in the cell really doesn't have the ability to do much change because it's so unstable. Now, there's a theoretical possibility, and I say theoretical very loosely here, that the AstraZeneca vaccine could persist in cells as double-stranded DNA. This whole concept of these adenovirus vectored vaccines are built off of the idea of gene therapy, So the idea is, if I want to experimentally express a gene in someone that you're deficient of, I hit you with a gene therapy virus or a gene therapy vector, and it expresses that protein or that gene in your cell, creating the protein for as long as that cell lives. It still doesn't integrate into your DNA, but in theory, it would persist. The big difference between an adenovirus vector as a gene therapy vector and a vaccine vector is, of course, the gene therapy vector, the body doesn't recognize that as foreign. In a vaccine like this, it recognizes the protein that's being created as foreign. And because of that, the immune response activates and kills the cell. So in theory, yes, you could have persistence, but the immune response prevents this. So are the vaccines safe, or do they cause adverse reactions? And I mean, I think the important thing here is to remember that every drug is going to cause some degree of reaction. Post-injection, post-medications reactions occur rarely from all medication. There's no real greater risk from vaccines. For some reason, vaccines always have a bad rap. But we look at drugs like Tylenol. Tylenol can cause liver failure spontaneously. You look at drugs like aspirin. Aspirin can cause bleeding disorder, exacerbate hemorrhagic strokes. So you have a lot of risks of these side effects from any medication. The number one thing that they're finding as a possible allergen is polyethylene glycol. It's something that's used in the mRNA vaccines to stabilize that lipid envelope, the lipid nanoparticle. So this is not a new chemical or drug additive. It's used in a fairly large number of medications. Just generally, it's never been used in vaccines. So this can cause anaphylactic reactions in approximately 5 out of 100,000 people, or a little less than that. So that is give or take 0.005%. So this is more or less in line with what we would typically expect as the relative risk of anaphylaxis spontaneously to anything. So it's not that it's increasing your risk of an anaphylactic reaction. It's just that if you give enough of an allergen to a large enough group of people, you will find someone somewhere who's allergic to it. The big thing that this vaccine certainly cannot do is cause or transmit COVID. There is not only is there not a living virus in this, there is not even a full COVID virion in this. So the ability for that virus to then cause any disease is very, very low. Well, it's zero, actually. The other really important thing is we talked about that alternate pathway, that pyroptosis pathway, where the cell says, all right, I've called for help and no one's coming to help me, so I'm going to kill myself and have a massive inflammatory response. The really cool thing about these vaccines is because we don't have any RNA replication, which we would have during natural infection, we don't activate one of the key pathways that triggers that. So the pathway that looks for that double-stranded RNA intermediate. So without that, we can activate all of those help me pathways, we can activate all those immune activating pathways without risk of going down into the potential severe inflammatory disease pathway. All right, so we talked about this, why do the mRNA vaccines need to be stored at -80 degrees? And I've gotten this from, the questions from a supply chain logistics perspective, all the way up to does this mean it's going to be injected into my arm at -80 degrees? It does not. So like we said, mRNA is highly unstable. It needs to be kept from deteriorating. So to keep it from deteriorating, it has to be kept frozen. And the colder it gets kept, the more stable for longer it will remain. So even the Pfizer vaccine, which has -80 storage for extended periods of storage, can be stored for up to, I believe, 30 days at -20, and for up to 5 days at 4 degrees Celsius fridge temp. Moderna is -20 degrees storage for up to 6 months. It can be stored for 30 days at fridge temp. Difference in technology is probably basically as simple as the mRNA is going to break down from the outsides in. All Moderna did was they put in what we call a poly-A tail, so just a large non-coding region at either side, that if it's starting to break down, it's going to break down this non-coding sections of the mRNA and not actually impact the gene itself in the middle. Both of these, once we reconstitute them, have to be used within 6 hours, right? So once you actually add the diluent and dilute it down, it's now a lot more dilute. It's a lot more at risk of breakdown, so it has to be used right away. But they certainly both have some degree of flexibility to allow for a little bit of work in how do we push this out from a supply chain logistics perspective. And they're certainly brought up to room temp prior to administration, or at least fridge temp prior to administration. The AstraZeneca, Johnson & Johnson, and Novavax vaccine. So AstraZeneca and Johnson & Johnson were those adenovirus vectored vaccines. Novavax is just a exogenous protein. So all they do is they create a whole bunch of that spike protein, collect that spike protein and inject it like that. These are much more traditional vaccines. They don't require anything special in the way of storage. They don't require anything special for time post reconstitution. They're managed a little bit more like traditional vaccines, so these are going to be a little bit easier to mass distribute. The The big thing here is, of course, that well, for one, these ones are not licensed yet in Canada, so we are all three, I believe, are in the application process. So it's just a matter of waiting for the license approval, at least as of today, which is the 23rd of February. So as more and more people are getting vaccinated or getting off the opportunity for a vaccine, there's the question of I have or I am, insert a comorbidity here, can I get the vaccine? And the big one that I get a lot is I'm pregnant, I'm breastfeeding. Can I get the vaccine? Because the original drug trial did not include pregnant or breastfeeding women. And actually, I believe it said, do not, for all participants, avoid attempting to get pregnant or attempting to conceive within 28 days of the second dose. And this is fairly generic language in drug trials. It's something that's pretty much buried in most drug trials, something to that effect. And it's just designed to take out any potential risk of external influence on the results. There's also a perspective of liability and risk side of things. So what we often do is with all of our vaccines right now, it's based off of the best practice recommendations from third-party investigators. And we in Canada use the Society of Obstetricians and Gynecologists of Canada as one of the, well, basically the guiding body to determine what's recommended for as treatments, medications, vaccinations, et cetera, during pregnancy and breastfeeding. Their recommendation has been that the risks posed by the vaccine are very, very, very low, and the potential benefits far outweigh those risks. So their recommendation is that all anyone who's pregnant or breastfeeding or attempting to conceive are still recommended to get the vaccine. The same can be said from a perspective of autoimmune disorders and immune compromise, where they're not contraindications of the vaccine. They were excluded from the drug trial. And very often what's done is, for example, an autoimmune disorder, it's taught to your rheumatologist and they'll determine whether or not to approve you or not. Most I've spoken with and most almost all of the people I know who've subsequently gone and talked to their physicians after this, it's been a yes, the benefits from the vaccine far outweigh the potential risks, so it's recommended that you go and get it. The only true contraindication is an allergy to the vaccine or a component. So anyone who gets a anaphylactic type response, those immediate hypersensitivity reactions to the vaccine, will of course be excluded from getting the second dose. Anyone who gets a non-anaphylactic response, so a delayed type hypersensitivity reaction, for example, should contact public health and speak to their physician prior to the second dose, as it'll be on a case-by-case basis based on the severity of your vaccine. But the only true contraindication is hypersensitivity to the vaccine or a known hypersensitivity to one of the components, like polyethylene glycol. So they've changed the vaccination schedule. How is this safe? And this kind of gets right back into that same concept of the drug manufacturers have a very narrow window that they test. They tested 21 to 28 days, and that's all they tested. And really the idea behind that was 21 to 28 days gives us fairly good assurance that our initial immune response to the first dose has peaked and subsided, and we should now be able to boost that immune response with the second dose. And it's really designed to make sure that we're not coming in too early, where we haven't actually created the responses from the first dose to even boost it onto the second dose. The evidence right now from third-party trials is that immunity after one dose is lasting at least out till 90 days. Likely it's even longer. I'd say most likely 6 months to a year is probably a good bet. But we're certainly seeing out to 90 days. Right now, Health Canada, as of right now at least, has approved pushing out to 42 days. I personally got mine at 35. I know a lot of people got their second dose around 35. But the evidence is rolling in right now that immunity from the first dose is quite effective. I often correlate this to things like the MMR vaccine. Anyone born before like the mid to late 90s only got one dose of MMR, measles, mumps, rubella vaccine as a child. If you then started in healthcare as an adult, you very often would have been approached to say, hey, you only had one dose of MMR, we recommend getting a second dose. The fact that you didn't have your second dose as a child doesn't mean that your second dose as an adult is less effective. What it means is that the protection that that first dose had given you may have worn off more so than if you had gotten a full 2-dose series as a child. So it's just delaying the boosting effect. So there's really no scientific reason why delaying the second dose would reduce efficacy. All it's going to do is reduce how long that immune response will potentially last for. So they have all these variants coming out right now. Are these going to make the vaccines ineffective? So the fact of the matter is that variants are going to crop up quite routinely. Viral mutation happens all the time. Coronaviruses are actually a little bit more on the stable side. They have the ability to do what we call proofreading. So as I'm going in creating a copy of the genome, if I put the wrong letter in, coronavirus can say, oh, take that out, put the right one in and keep on going. Whereas a virus like influenza just says, completely ignores it and just keeps on rolling and hopes that the mutation doesn't kill the virus. Very often they're lethal to the virus. When you have a mutation that provides genetic advantage, these are mutations that are going to accumulate and going to stick around. So right now, what we're seeing is a few very commonly conserved mutations. The most common one we're seeing right now is the spike receptor binding domain, so the portion of spike that binds to that ACE2 receptor, a mutation called N501Y. So the amino acid at site 501 has changed from an asparagine N to a tyrosine Y. So this has been shown to not be antigenically novel, which is really good because what that means is that any antibodies you have that bind to spike receptor binding domain and neutralize that virus will still bind to this mutant. The non-RBD mutants, so things like 69-70 deletion, where the amino acid at site 69 and 70 are deleted, because these aren't going to be receptor binding domain mutations, they're also highly unlikely to have any impact into the antibody immunity and should not impact how effectively you have immunity. What they are finding is a mutation in the receptor binding domain called E484 may have about a 10-fold reduction in antibody recognition. So what that means is not that this mutant is immediately susceptible to reinfection. What it means is that your antibodies will slowly start to wane faster, not faster, but the waning of those antibodies will become more clinically significant sooner. So this is where you're at risk of potential reinfection, either after an initial natural infection or after an immune response from a vaccine. It's not one that you are immediately, or at least the clinical evidence isn't showing immediate susceptibility to reinfection. It's more that around the 6 months to a year, you're going to be susceptible to reinfection. The important thing to recognize is the whole cellular immune response remains unchanged. These are a lot broader and a lot more resistant to change. So if we think of spike as a fairly large, complex protein, the receptor binding domain is just that very little top there. So that's the point where you're going to have an antibody bind to neutralize the virus. If you change that and the antibody can't bind, then the virus can enter into the cell, and that's where you can cause infection. But it's still a big chunky protein. So just because you change this one little bit, once it's in the cell and it starts getting truncated and chewed up and looked at from T cells, they're going to look at the protein from multiple different angles. And by looking at it from multiple different angles, if this portion is changed, and this portion is changed, and this portion is changed, they might still find that here, here, and here are unchanged. And those are still going to be enough to activate those cytotoxic T lymphocyte responses. So that's where there's still going to be some degree of cell-mediated immune response that help reduce the severity of infection. So with that in mind, it kind of leads right into the idea of, will this be an annual vaccine? So immunity from neutralizing antibody sera. So I have antibodies in my serum that will neutralize the virus, should last for about 2 years, barring any dramatic changes like variants. As those start to wane, our cellular immune responses still last a lot longer. And like we said, these are what protect you from severe disease as those antibodies dissipate. So what's likely going to happen is every couple of years, your antibodies will drop off, you get reinfected, and your cell responses stop you from having a severe disease, but that reinfection will now reprime your immune response. And you'll taper off and reprime your immune response after a couple of years. So in essence, what that will do is the immunity in the population will attenuate the severity of the virus and the transmissibility of the virus, but it will stick around as an endemic mild virus, not requiring annual vaccination, but seeing that kind of seasonality to spread and every couple of years susceptibility to a reinfection. I like to think back through the coevolution of humans and viruses. At some point in the millennia preceding 2020, humans had evolved with what we currently consider a seasonal coronavirus. At some point in that human evolutionary process, seasonal coronaviruses would have been a completely novel pandemic-like coronavirus. So until we get that degree of underlying immunity within the population, it had to have had that pandemic response kick through and drive that immune response. So that's what we're essentially seeing right now, is we're writing the history of getting this particular lineage of coronaviruses and hopefully seeing cross immunity across all bat origin coronaviruses and getting some degree of cross protective immunity to that lineage of coronavirus. So as we have that attenuation, we get that endemicness, we get that seasonality to it, that much more mild disease, but the pandemic nature of the virus dissipates. So as I'll wrap up with the last couple things I'm getting. So if I get vaccinated, can I still transmit COVID? And the answer is it depends on how good your immune response is. So if I have neutralizing antibodies and I am physically incapable of getting infected, so we're looking at about 50% immunocompetent adults 7 days after dose 1, upwards of 90% 14 days after dose 1, and about 95% or so 14 days after dose 2. Those groups should be, in essence, largely immune from initial infection. If I can't get initial infection, I'll never have enough virus in my system to truly be infectious, so I should not be able to transmit COVID. That said, if I'm in the group that isn't in that category, I can still have virus in my system. Because I can still have virus in my system, but I have those cellular responses, I might have very mild or asymptomatic disease. So I might still be able to transmit the disease to others. Now, arguably, the paradigm of transmissions is likely going to shift, where because you're looking at lower severity of disease, lower viral load, your severity and risk of infection to non-household or non-intimate contacts is going to be a lot lower. But that remains to be seen right now in clinical application. The other one that I've heard very recently is, can I take Advil Tylenol after this vaccine, or will it reduce efficacy? This was a bit of a weird one to me. I think the idea came from the concept that Advil and Tylenol have anti-inflammatory properties. So if you are taking an anti-inflammatory, can you potentially immunosuppress yourself to the point where you won't develop a strong enough immune response? And the short of the answer is Advil and Tylenol are not nearly strong enough anti-inflammatories to truly make an impact in vaccine efficacy. Looking at Advil as an example, the true anti-inflammatory dose of Advil is well above what's actually indicated on the bottle. So unless you're swallowing a whole bottle of Advil, the realistic impact is going to be zero. So some of the other questions, just to kind of finalize things off here, the last one I've gotten is as we start shifting towards potentially multiple vaccines being in the market at the same time, what happens if I got Pfizer as my first dose and Moderna as my second dose? Well, I can absolutely guarantee that Pfizer is not going to advise it. They might have a vested interest in wanting people to make sure that they're also buying their vaccine for the second dose. So I think there's a conflict of interest there. But Pfizer and Moderna are such virtually identical vaccines. From a scientific perspective, the reality is these are highly unlikely to have any dramatic impacts. With that, I hope you've enjoyed this session. Certainly, if there's any questions, I'm always happy to reach out and address them. I realize I don't have my email listed on this presentation, but my email is kstinson@smgh.ca. Always happy to answer any questions you might have and do my best to help spread some knowledge and spread some education. With that, thank you very much for your time, and I hope you enjoyed this talk.